angles, well, actually, as I introduce them, they'll actually be called special triangles, but I'm used to calling them special angles because we'll use the angles in the triangle. But that's neither here nor there at this point in the lesson. Reciprocal trig ratios. Some new friends to play with. These are called the reciprocal trigonometric ratios. You may have never seen them before. You may feel like I'm just making up stuff as I go here. Cosecant of an angle is equal to 1 over sine of that angle. And if you think I've wrote an extra letter there, I haven't. I'm going to show you the abbreviations in a minute. We're not going to write cosecant every time, just like we don't write sine every time. Then secant of an angle is equal to 1 over cosine of the angle. And then finally, cotangent of an angle is equal to 1 over the tangent of that angle. These words have very specific meanings, actually. You can draw a picture and talk about the secant, the cosecant, the sine, the tangent, the cotangent. You can do all those things, but we're not quite there yet. So if you just think that these names have been invented to torture grade 10 and 11 students, you shouldn't believe that. But I understand why you might believe that at this point, that these are just crazy names. There is an explanation for the names, but it takes a while to get there. We're just starting our trig journey here, and I can't really explain the name. Well, maybe I can. Have you seen the word tangent before? Have you used tangent in one of your classes? So maybe you just have a little bit of knowledge of what a tangent is. And secant might have come up as well. And these words will come up in later courses, and then you'll start to see why they're called these things. But we use abbreviations for these. Cosecant has a weird abbreviation. CSC is 1 over sine. You're used to calling it sine, not sin. Especially not at our school. You wouldn't call it sin. Sine, it's pronounced. Secant has a 3-letter abbreviation, and this one, you're used to calling this cos. People call it cos all the time, but it's cosine is proper name. And then finally, cotangent. Hopefully that doesn't intimidate you too much. You're like, okay, so if I've got the sine of an angle, I can go 1 over that and get what you're calling the cosecant of that angle. But here's some bad news. Come test time, you have to have these memorized. You have to know which one matches up with which. Here's my trick to memorize them. Cotan's easy, right? Cotan goes with tan. It seems like they were being kind when they called that cotan, because it would go with tan. These ones, the letters go opposite. That's just my memorization tool. That has no basis in math or language or anything else. There's no reason for that. I just notice that cosecant's with sine, C and S. And over here, secant and cosine, C and S. All right, so that's my memorization tool. But that doesn't explain anything about what's going on. That's just how I remember them. Well, that's all for the first slide. I paused for questions, but there's not much to question. It's just me telling you about some new trig ratios. You thought there was only 3. You left grade 10 thinking sine, cos, tan. As it turns out, there's 6. But the other 3 are just reciprocals of these. I'm saying reciprocal, but you might be asking, why are they called reciprocal? And I'll show you why. Here's how come. Let's talk about, first, cosecant of an angle, which is 1 over sine of an angle. But when we're finding sine of an angle, we're finding the relationship between 2 things. Which one's sine? What's the numerator and denominator of sine? Yeah, maybe you're expecting a more difficult question. I wasn't trying to be difficult. This is 1 over opposite over hypotenuse. And this kind of fraction annoys mathematicians, to have fractions inside of fractions. And we can always get rid of it. We can always change that and get rid of the fraction inside a fraction. And one way to do that is just to write this as a division question. and use what we know about dividing fractions to simplify the situation. What was the rule for dividing fractions? Yeah, flip it and change it to multiply. So what I'm going to do is change this to 1.
Mr. Todd?
Hello?
Hi, is Angela in class?
Yes?
Can she come see Miss Ronson?
Certainly.
Thank you.
So once it's written as division, your fraction rules come back into play, and I got 1 times hypotenuse over opposite, and 1 times anything just stays the same. So the 1 times doesn't matter anymore, and I get hypotenuse over opposite. Now think about that for a second. Sine is opposite over hypotenuse. Cosecant is hypotenuse over opposite. I'll switch colors here and go, it is sine flipped. That's all that's happened there. We're just flipping the trig ratios we had before, and the fancy name for flipping is reciprocal, giving you a much more handy definition of these things. They're all just the flip version of each other. I'll do it once more, the whole procedure once more, and then for tan, we'll just use the shortcut, okay? Yeah. If I want to do secant of an angle, that's 1 over cosine of the angle. And cosine is adjacent over hypotenuse. And mathematicians do not love fractions inside of fractions. It's too confusing with what's going on. And we always have our fraction rules as long as we're willing to write this as a divide first. And after we write it as a division, we can use our fraction rules to say, okay, that's 1 times, here's where the flipping comes in. Because it's dividing, it becomes flipping. So it's not magic or anything like that. That's just what division does. So I get hypotenuse over adjacent. And now I'll write my grand conclusion. It's cos A flipped, and the fancy word for that is reciprocal. Do you remember the words reciprocal? Did that come up before? Maybe you didn't use it enough. It's not really familiar. That's okay. So now, instead of going through all that, cotangent of A. So sine is opposite over hypotenuse. Cos is adjacent over hypotenuse. That means cosecant is hypotenuse over opposite. Secant is hypotenuse over adjacent. Can anyone take a shot at cotan A of what it's going to be after all that? Adjacent over opposite. All of that to see why these are called the reciprocal trig ratios, because you can just flip the corresponding ratio and get the reciprocal ratio. Not bad so far. Yeah. But do you have any questions about that? Do you need more time? So 2 of them I showed all the math for 1 over, and that's true 1 over anything. Anytime you go 1 over something, you're just going to flip what's in the bottom. That's going to happen every time you see that situation. So this one says find the 6 trig ratios for the given triangle. So the idea is I'm going to go sine theta equals opposite over hypotenuse, which is 3 over 5. I hope that's okay. I hope you're like, yep, that's good. I can do that. They're not asking to find out the angle. They just said find sine of theta, and that's 3 over 5. I'll do the 3 easy ones, okay? The ones that you knew before you came in today. Cos theta is adjacent over hypotenuse, which is 4 over 5. And tan theta is opposite over adjacent, which is 3 over 4. There. I could have done that when you came in today, and hopefully you would have been like, yep, that I got. But this said find the 6 trig ratios, which is big news today. There's not just 3, there's 6. So sine, don't peek. See if my memory tool is awesome. Which one goes with sine? What letter is it going to start with? CSC, good. He's sort of on it already. CSC of theta would be hypotenuse over opposite, which is 5 over 3. A very fair question would be, why do I care? That's going to take a little time for me to be able to explain why do I care. The big answer is sometimes we want the fraction the other way around for a certain question we're doing. Okay, so what goes with cos? Secant, it's pronounced. I know it says SEC, that's just the short form. And so that's hypotenuse over adjacent, which is 5 over 4. And then finally, cotan theta, which should be adjacent over opposite, which is 4/3. I must tell you, my grade 12s, I don't think memorize these like this. They jump from here to there when they're doing cosecant. They just go, okay, well, if sine's 3/5, then cosecant's 5/3. I think that's the way most people handle it. You don't have to do it that way, but I'm just writing out the full definitions here in my example. Do you have questions there? Would you like more time there? Is it okay? Example 2. In triangle A, oh, this time, very similar question, except I've got to draw the triangle myself this time. So here I come with my right angle triangle. But if you fall asleep, this question does have the smallest curveball ever in it. In triangle ABC, A is the 90, so there's A. AB is 12 and AC is 5. This bothers people when they have freedom of where to put B and C. But 90 matters, but you'll get the same answers. If you put B up on the top and C down here, you'll get the same answers as if you put the C in the B. It won't matter which way you do it. I usually go clockwise, but there's no good reason for that. That's just the way I do it. Yeah. So then AB is 12, so this is 12 centimeters over here. And AC is 5 centimeters, that's down here. And it says find the 6 trig ratios. No problem. Same as the last question. Sine, of the acute angles. Hold on. More work. That's not the curveball, but more work. I've got to do B and C. Ooh. So I'm going to divide my page up here and here. And I'll do B here. I'll do the 6 trig ratios for B, and then we'll do the 6 trig ratios for C. So first, sine of B is opposite over hypotenuse. Now be careful, if we're using B, which side's the opposite if I'm using angle B? The 5. That'll change in the question. If I'm using B, 5's the opposite. I'm going to label that temporarily on there. I'm going to know the code. For B, this is opposite, and this is hypotenuse. Yes, if I'm using B. Not a hypotenuse. Adjacent. Thank you. Adjacent. And this is hypotenuse. Good. So now my job is to go opposite over hypotenuse. So opposite is 5, and hypotenuse is 13. I don't see a 13 on there. Where are you getting that from? Yeah, see, there's the little curveball. If you've got 2 sides of the right angle triangle, that's all you need, because Pythagorean theorem will take care of the rest. So hypotenuse squared equals 5 squared plus 12 squared. Hypotenuse squared 25 plus 144. Hypotenuse squared equals 169. And so the hypotenuse is the square root of 169, which is what he said, which is 13. Did you know that in your head, or what did you do to find out 13, by the way? Okay, good. So you did all the steps there. Well, now the rest of this becomes easy. Once I've got that side, sine of b is opposite of hypotenuse. Cos of b is adjacent over hypotenuse. Do you have to write adjacent over hypotenuse when you're doing these? No. If it's possible to get so good at these, you don't need to write down that intermediate step. But I'm trying to teach well here and write down where I'm getting these answers from. So cos of b is 12 over 13. And tan of b is opposite over adjacent, which is 5 over 12. That should have been, that's like from grade 10, that much. Grade 11, now we can do this. We can do cosecant of b, which is hypotenuse over opposite. Do you have to write that? No. You could totally just flip over sine. That's the whole point of reciprocal ratios. You can just flip sine over. And then secant of b is hypotenuse over adjacent, which is (13 over 12). And finally, cotangent of b is adjacent over opposite, which is 12 over 5. Any questions there? Now I'm going to switch colors and do the same thing because it says find the 6 trig ratios of the acute angle. So I got to do B. I also got to do C. Now look carefully here, because if you're getting all this and you're like, okay, so I just flipped them all over. That's what you said so far today. I'm like, yeah, but some people ask some questions in the homework, and this sort of messed them up a little bit. If I'm going to use C, the hypotenuse is still called the hypotenuse, but now this isn't called adjacent anymore. This one's called the opposite side, and this one's called the adjacent side. And if that bothers you, maybe it should, but let's just do my example again. Which side of the classroom are our windows on? Are they on the right or the left? He's seeing through my question. He's saying it depends on how you look at it. For you, those windows are on the right. To me, they're on the left. That doesn't mess most people up. They're like, okay, yeah, that makes sense. But it's true in triangles too. If I look from B, then 5 is the opposite. If I look from C, then 12 is the opposite. So it depends on where you're looking from. I'm not trying to mess you up, really. I'm trying to make sure it's clear, so if you decide to use a different angle, you know to relabel the sides. So then when I do C, when I do sine of C, now opposite over hypotenuse is 12 over 13. And cosine of C now is 5 over 13. Now I don't want to get sidetracked here, but it's quite possible after doing last night's homework, like, well, that's trig, isn't it? Well, how's there 2 chapters of trig in grade 11? We're doing all the trig. I did all the trig. Sakatoa, Pythagorean theorem, we're done, right? No, way more trig coming. And some of the more trig that we'll look at eventually is, look what's happened here. Look at sine of B and cos of C. They're both 5 over 13. There's some kind of relationship here between sine and cos when you change the angle. So, not today, but I just noticed that in here. And then if I do tan of B, or sorry, of C now, that's now my new opposite over adjacent. That's 12 over 5. Now look down the list and see if you can see in the B's 12 over 5 somewhere. Cotan of B is the same as tan of C. Ooh, that's not today, but there. All I'm doing that for is to make you go, there's more trig coming, folks. We're just getting warmed up on trig. There's a lot more to know here. Okay, so then, are you going to let me away with it here? When I do C? No, I'm not letting me away with it. I'm telling you that when you're doing these questions, you don't have to write everything I did in the middle box there. That was just me teaching. When you go to do cosecant of c, you are more than welcome to just look up at sine and flip it over. Yeah, that's a perfectly legitimate move. And secant of c is 13 over 5. And cotangent of c is 5 over 12. You're just doing the reciprocal of the primary 3 trig ratios. Any questions there? Okay, in review, Mr. Todd, so far what you did is you came out with new names for the flipped versions of sine, cos, and tan. And you reminded us that we can use the Pythagorean theorem when we need it, and that opposite and adjacent are sort of dynamic. They can change based on which angle you're going to use. That sums up what I've said so far, for sure. Do you need more time there? If cosine of theta is 2/5, find the other 5 trig ratios. Same type of question with a different setup. So here comes my right angle triangle. I'm going to put theta on there. I'm going to put the right angle on there. If I'm using theta, then this is the adjacent, 2. And this is the hypotenuse, 5. I don't know, give it a shot. See if you can do the other 5 trig ratios. Now, see if you challenge yourself to try to remember them.
Like she doesn't have any calculator. Like I don't know how to use this.
The teacher in the learning center doesn't have a calculator.
She does, but
She's not taking math class. You're taking math class.
yeah. Oh,
That's a perfectly good calculator.
no,
but
because this one doesn't have the thing. Like I tried punching it all in.
the thing, what thing?
Like adding like the asymptote to like a thingy to go down.
It does. This one does all the things that one does.
This one, I don't think that's I'll bring this one.
One option you could do would be to get a calculator. That would be my advice here. And a pencil, yeah. How'd it go? Tell me. What can you do? What can't you do? What did you do first? Just how I didn't do anything. I was still working on it. Oh, okay. I'll wait. You think he'll retune my calculator to me? No. No. Time will tell. I'm going to do one step for you and show you one thing just in case. I don't want you to write a bunch of stuff that is not what I'm after here. Use that, please. If you found it out to be the square root of 29, then we got to talk. I'm quite willing to answer that question. I'm not going to call it a bad question. I'm just saying we should talk. If you wrote down root 29, we should talk. If you went to decimals, don't. Use the square root for now until we get clear on why we want decimals and when. Now I'm going to write down the answers. I encourage you to do it yourself and then look out at my answers. But I'm going to start putting them up there so you can look and check yours as you go. Do you want more time to try it on your own? Still trying? The questions that might come up are, why did you subtract with the Pythagorean theorem? Can anyone answer that in a simple way, Ben?
Because we're not finding c squared anymore.
Yeah. The hypotenuse is the biggest side. We add to get to the hypotenuse. So we must subtract to get to the other sides. That might be a little quirk in the Pythagorean theorem you might have forgotten about. Next, is decimals fine? And the answer is, I don't know. Like, I really mean I don't know if decimals are fine. So that's why in math, as mathematicians, we don't go to decimals unless we've got a reason to, unless there's something about the question that tells us it's okay to go with decimals. Third question. Did you do this? To get rid of that radical in the denominator. Somewhere along the way, we talked about we don't like radicals in the denominator. And we haven't really explained that very well, explained why we don't want radicals in the denominator. And it has to do with combining with other things. If we're going to combine with other things, radicals in the denominator are going to be in the way for that. So that's one of the reasons. So get used of getting rid of that radical in the denominator by multiplying both the top and bottom by whatever the radical is. And that you can be annoyed by, and I totally get it, that you're annoyed by that. Do you have any questions now? Would you like more time? We're halfway. I think it's halfway on mine and halfway on yours. You're done the front page, first page front and back now? Now we got to do a second page front and back. Yeah. It's okay? More time? Good. All right, special triangles. There are some very special triangles in this world. I've already used two of them in the lesson. Teachers and students love this triangle, the 3, 4, 5 triangle. It's one of the triangles where the pairs work out nicely, no decimals. 3, 4, 5. 3 squared is 9, 4 squared is 16. That adds to 25 and you get a 5 there. So I'm not going to say much more about the 3, 4, 5 triangle because teachers use it all the time. You wonder how they make up questions. Like when you're first using the Pythagorean theorem, a teacher can usually make up a whole bunch of questions where the numbers work out nicely with no decimals. And lots of times, what they're using is the 3, 4, 5 triangle. So let me show you. Let's say I was making up a question for a grade 7 student who was asking me some questions. And I go, okay, let's make up a new Pythagorean theorem question. But I want it to work out with nice numbers. So I draw a right angle triangle and watch what I'm going to do, which might blow your mind a little bit, actually. I'd look and in my mind, I'd think 3, 4, 5, 3, 4, 5, 3, 4, 5. Oh, this will work out nice. Because what answer are they going to get if they do the Pythagorean theorem? 50. I've just taken the triangle and blown it up 10 times, and now this will come out to be a 50. Or I could do this. This takes a little more thinking, so stick right with me so you understand why the 3, 4, 5 is so special. So when we're first learning Pythagorean theorem, so I'm going to do, let's see, I'm going to use 15 and 12. So this would be a 9, because I just took it and multiplied it all by 3. So you could use any number you want and make up new questions where they work out as whole numbers. That's why 3, 4, 5 is so special, because it's a family of triangles, really. It's everything that's 3, 4, 5, or multiples of it. There's another special triangle that I didn't put in this part of the lesson that's often used, is this one here. It came up in the 5, 12, 13. 5, 12, 13 is another called a Pythagorean triplet. Ooh, fancy name, and just means it works out to nice whole numbers, and any multiple of that will work as well. So you can make up a whole worksheet of these for grade 7 students, and they never notice what you're up to, because you're just multiplying by different numbers and making up basically 2 different questions with all, and you're just multiplying them into families, okay? So that's a famous triangle. It might be the most famous triangle in math, is the 3, 4, 5 triangle. In fact, tradespeople use it all the time to build right angles. Like when they go into a room, and I'm oversimplifying it, by the way. This isn't quite as easy as it is. But if they want to lay 2 brick walls like in the corner here, you want to get it at a right angle. So what they do is they measure out 4 feet that way, 3 feet along this wall, build a 2x4 that's exactly 5 foot long. And if they put that in the corner, they know it's going out at a right angle. They use the 3, 4, 5. So that triangle is known well by tradespeople. Yeah? There are other ways to do it, of course. 2 triangles that keep values exact. That's what these things do. Let me get the highlighter out. I'm going to get not just the yellow highlighter, I'm going to highlight that title in red. Stole that trick from my daughter, who loves notes, loves highlighters, loves study notes, loves all that kind of stuff. She's into it. And when she highlights something in red, that to her, that's like, got to know this. Got to have this ready to rock and roll. And I highlighted in red to know that why are these triangles so special? They keep things exact. Here they are, and my demonstration of where they might have come from. I'm not sure exactly where the development was exactly, but let's pretend we back up 2,200 years or so to the time of Pythagoras, and we know about right angle triangles, and we know the Pythagorean theorem. That's all we know so far. And we're just sitting around one day, all the group of us, because that's what they had time to do, was sit around all day and think and go, what's the simplest triangles we could come up with? So somebody said, well, the simplest triangle I can think of would have 1 on this side and 1 on that side. Let's talk about what else it would have if we start with 2 1s. Well, the first thing I notice is I can get the hypotenuse by going c squared equals 1 squared plus 1 squared, which is 1 plus 1, which is 2. So that third side will be root 2. Now that is a little bit awkward. My very simplest triangle that I could think of with a 1 on both sides had root 2 as its hypotenuse. So that's not quite as simple as I was hoping for, but not bad. 1, 1, root 2. If there was a Hall of Fame for triangles, and you were trying to decide who the GOAT was, this one might win in math. It's in heavy competition with 3, 4, 5. The 1, 1, root 2 triangle. Because it gets better. I know the angles. I don't have to do any math to know the angles. This thing is an isosceles triangle. So I know what those two angles have to be. Can anyone tell me what the angles must be? Equal. They must be equal, which gives me everything I need to know. These two angles are equal, which means they got to add up to 90. So this thing will add up to 180. They're both 45s. That's why this triangle is so special, is it's mostly simple. It's about the most simple triangle I can come up with. It's got 1s, it's got 45s. It's got one little weakness, is the hypotenuse is root 2. So somebody else goes, well, okay, I'd like to make a special triangle. I think I can do a little better than your special triangle. Maybe mine's the simplest triangle. And they go like this. They go, okay, instead of 1 and 1, yours came out to root 2, which wasn't as simple as we could be. I'm going to go 1, and I'm going to force a 2 to be there. So this is the 1, 2 triangle. And they go, well, now I'm going to use Pythagorean theorem to find out what my third side is. And it's 2 squared minus 1 squared, because I'm not going after the hypotenuse. And I get a root 3 there, which is mildly disappointing, because you're like, well, I guess this triangle isn't simpler. It's still got a root in there. And the people that were a fan of the 45-degree triangle, but well, what are your angles? I'm like, I'm not sure what my angles are. Let me find one of these angles. Let me find this angle A. And to find A, I'm going to go cosine. Cosine of A is adjacent over hypotenuse. And I'll get out my calculator 2,000 years ago. They'd probably get out a protractor and measure this carefully, is what they do. So take your calculator and type in cos inverse of 1 over 2, and hopefully be wowed a little bit. What'd you get? 60. Not 61, not 60.2. 60. Well, that's pretty cool. All I did was make a triangle with 1 and 2 in it, and the angle here was 60. Meaning this angle is pretty easy too. What's the angle up in the top left corner then? 30. Two pretty nice little triangles. The two simplest ones, I think, that the universe came up with. 45s, 30 and 60, and the sides are sort of simple. 1s and 2s and 3s, some of them rooted. You know, there's a couple of roots in there. We do study them because they're neat, but in grade 11, that's what they're going to accomplish, is keeping values exact. We won't have to round when we're using these things. We can still keep our future together of working at Apple or Google, not at Samsung or something. You know, we can still work at the big places if we know how to keep things exact. Sort of a joke, sort of exaggerating, but sort of not. You know, if you want to build iPhones, we can't be rounding things off all the time. We got to have exact answers, and I'll show you what I mean in the remaining examples. So, two triangles that are very special, and in my title I called it giving us a bunch of angles that are special. 45 is a special angle. 30 and 60 are all special angles. Okay? Because they were in the special triangles. What can we do with it? I'm going to jump right into the deep end of these questions and go, using those special triangles, you can find the exact value of sine 45 times cos 60 times tan of 30. Here we go. This will not be difficult. This will not be difficult if we know our special triangles. Scary monster. Scary monsters. You've got to find a way to memorize these two triangles. And I've tried to present it in a way that I'm like, oh, I can do it like Mr. Todd did. All I got to know is 1, 1, Pythagorean theorem to get the third side. Or I got to know 1, 2, Pythagorean theorem to get the third side. That's all I got to really know. I wouldn't do it that. I'd just memorize them. I'd just test myself and make sure I have them. Sine of 45. If you know your special triangles, that's really easy. To get an exact number, I don't need my calculator. See, when it says exact, it means two things. It means no rounding, No calculator. But it's easy if you know your special triangles. Sine of 45. Opposite is 1. Hypotenuse is root 2. 1 over root 2. Cosine 60. If you know your special triangles, it's real easy. I don't have to round. I don't need decimals. I can just look at my special triangle and go cos of 60, adjacent over hypotenuse, 1 over 2. And then tan of 30. Go over to my special triangle and I go, for 30, tan of 30 is opposite over adjacent, which is 1 over root 3. I'm not done, but the worst is over. It's exact. It's not decimals. I never had to touch my calculator once. I know some of you had the fancy calculator. And when you type in sine of 45, it says, it doesn't say 1 over root 2, but it says something very helpful. I know you got help there. But the point of these type of questions is that you can do them without your calculator. So I'll do a little simplification here, and then you complain. Seriously, complain if you don't like what I've done or if you don't understand what I've done. Because this is supposed to be essential numerical skills in grade 11. And if it's not, let's talk about it. So I'm almost done the lesson. So if you've got questions here, if this is what we want to talk about, then let's talk about what I did there. I'm glad to take the time to over-explain what happened there. Do you have questions? Ben?
We did, for that top one, we did root 2 multiplied by root 3 to get root 6.
Root 2 times root 3.
And that 2 in the middle on the denominator, one of the is 2 out front.
Yes. This 2 is now out front, and I went root 2 times root 3, because radicals can be collected. It was a long time ago now, back in September, when we talked about radicals and stuff like that. And we've done no practice on it since, giving you very little chance to retain that. But there, I wrote it up here. When you have 2 radicals like that, you can multiply them together, if that's better, or you can break them apart, if that's better. That's what we did a lot of, was breaking them apart. Good. That explains that line. Does this line ring a bell? To get rid of radicals in the denominator, you multiply top and bottom by whatever the radical is. And then, so root 6 is now on the top. And the bottom I get root 6 times root 6, which is root 36, but misses the point. If you multiply root 6 times itself, you get 6. But you could put root 36 in between, if that helps you to understand. Now, who's got a Casio calculator? Type in sine 45 times cos 60 times tan 30. And press equals and see what you get. Well, it's not just a Casio thing. Some of you have a sharp calculator that can do it. But I just know a lot of you have the Casio. That's why I said that. Root 6 over 12? Nice for checking answers. Now, if you get this question on the test and you write root 6 over 12 and move on to the next question, how many marks do you suppose Mr. Todd's going to give you? 0. I can get anybody to type things into their calculator. That's not the point of grade 11U. I want to see this work. Yes? You could get it wrong and get most of the marks if you're showing me the work that this course requires. The calculator's for checking. I know it's a wonderful calculator. It's great stuff, but it's for checking only. Questions there? Well, if you understood that, question 2, which might have intimidated you at the start of the class, if you had looked at question 2, it might have intimidated you, should be like, oh, that's no problem. Yeah, when we look at it. It says sine squared 45 plus 2 sine 30 secant 60. The only thing I got to show you here is what sine squared 45 means. Mathematicians got lazy, and now you got to pay the penalty. They got tired of writing this. Because sine 45, although you don't know it yet, gets squared a lot. Anytime you got a sine, you often square it. It's not clear why that's going to happen yet. And so mathematicians got lazy, and they got tired of writing the brackets and the squared on the outside of sine. So they sneak the square into the middle of sine right there. See it, sine squared 45? That's completely whacked at this point. I get that. But that's what that means. And so you want this transition. So every time you see sine squared 45, it means take sine of 45 and then square it afterwards. You should be annoyed by that. You're like, oh. You're going to like it as time goes by. That's a nice shortcut to write things. But it's okay if you think that's completely weird right now. What is sine 45? 1 over, he's almost got it memorized already. That's what's nice about the special triangles. 1 over root 2, yeah. Sine of 30, I don't know if that's a memorized one. Here's what's supposed to happen by the end of the chapter. I hand out the tests, the day of the tests, and you immediately draw 2 triangles up in the top corner by your name, the 2 special triangles. You go, there. Now they're there. Whenever I need them, I've got them ready to go. Sine 30 is 1 over 2. Did you have to look, or did you already sort of have it memorized? Some people can, I don't know. I've never been able to memorize them just quite like that, but some people can. So sine of 30, opposite of hypotenuse, right off the triangle. If you got the triangle memorized, very easy. If you don't have the triangle memorized, things can get quiet in a hurry on test day if people don't have the triangles memorized. What was the next one? Secant 60. Here's what most people do. When they see secant, they go over here and they go, hold on, let me get cos of 60 first. And they do a little side thing here, cos of 60, and they look at their special triangle and they go, cos of 60 is adjacent over hypotenuse. That's 1 over 2, and so then they write 2 over 1 in there. Other people do it another way. They go, okay, secant, that would be hypotenuse over adjacent, and then they go to their special triangle, hypotenuse over adjacent. And you can do it that way. That's fine too. Now I'm going to write a line that might scare you, but then I want you to stare at it for a little while before you ask a question. I'll answer questions about it. But I want you to stare at that long enough that you either have an aha moment and go, oh, I get that. Or at least you understand what you don't understand about it. What a weird sentence that is. Tell me.
Squaring the root.
That's what squaring is. It undoes roots. So 1 squared is 1, but root 2 squared is 2. How about 2 times 1/2? You're multiplying by 2 and you're dividing by 2? Another example of inverse functions going at it, and then 2 over 1 is 2. Maybe you looked at these 2 and multiplied those together. Either way, you get a 2. Now, just a little fraction work on a Thursday. I want to add 2 fractions. So first I'm going to think of the 2 as over 1. Then I'm going to get a common denominator and add those together to get 5/2. Giving a slight example why we do trigonometry. Look at this disaster of an expression. Sine squared 45 plus 2 sine 30 secant 60. And with our trigonometry skills, we find out, oh, that's equal to 5/2. Isn't that better? Isn't that more simple? So this trig we're doing is about simplifying things. And if you type sine squared 45 plus 2 sine 30 secant 60 into your calculator and press equals and get 5/2, I will give you 0. I'm like, oh, that's very good. I could have got my 7-year-old to type that into the calculator. That's not a problem. I need you to show me the trig. Incidentally, if you did want to type secant into your calculator doesn't have a secant button. You'll have to type 1 over cos 60. If you did want to type that into your calculator. Okay. More time there? Prove. Oh. No word strikes more fear into the heart of mathematicians than the word prove. You've got to show that this is true. So, if you haven't done any proofs before, I expect you haven't done any proofs before. So this is our first time for the proof. Here's what proofs are supposed to look like. You go over here and you go left side And over here, I'm going to do a bunch of work on the left side. I don't know how much work I'm going to do on the left side. And I go to the right side and go, okay, I'm going to do a bunch of work on the right side. And hopefully when I get to the bottom of the page, they're equal to the same thing. Left side, cos 60, secant 30. Please don't underestimate what I've done there. That is the basics of proofs in mathematics right there. You write what's on the left side, you write what's on the right side, and then I'm going to do whatever in math I know, and hopefully the last line, the things I see are equal, because I don't know that cos 60 secant 30 is equal to tan 30. I don't know that in my head, me personally. But with a little work, maybe I can find out. Generally in proofs, we start with the more complicated side, because maybe it just comes out to this. It's a little more efficient to do that. Cos 60, where do I get that from? It's a special angle, so it's in a special triangle. So as long as I know my special triangles, I go back to cos 60 and I go, okay, cos 60 adjacent over hypotenuse. That's 1/2. And then secant 30, again, I might potentially with secant 30 do a little side thinking and go, well, I'll get cosine 30 first, and then I'll flip that over. Cosine 30 is adjacent over hypotenuse, which is √3 over 2. So what I get is 2 over √3. So I'm going to put those together, and I get 2 over 2 √3. And the first thing that happens is the 2's cancel. And maybe you think you've done the best you can do. You haven't, but maybe you think you have. So then proofs look like this. You go, well, maybe I'll work over here for a little while, and I'll find out what tan of 30 is. And tan of 30, I can get off my special triangle. Here's tan of 30. Opposite over adjacent. 1 over √3. And I'm done my proof. You go, well, don't you have to get rid of the √3s? Yeah, but I accomplished what they said to do without doing that, which might scare you a little bit. No, you said get rid of the roots, Mr. Todd. I'm going to get rid of the roots. Okay, go ahead. It's fine. But there's maybe some wisdom coming about roots in the denominator. Like, well, maybe when do we want the root gone? When don't we? Okay, I'm not changing the rules. I'm not. I'm just saying in this particular situation, I was done. But to make sure no one goes home unhappy, I will do that to both sides. Times √3 over √3. I get √3 over 3. And over here, I times by √3 over √3. And I get √3 over 3. And everybody goes home happy and not thinking I'm about to change the rules, because I'm not going to. And we write something like this at the end. There's lots of things you can write when you've done a proof. Therefore, left side equals right side. Therefore, cos 60 secant 30 is equal to tan of 30. And mathematicians have a whole bunch of special symbols they use when they prove something. So if you want to be really cool, you wrote a little double line like that. Or sometimes they're like a little square like that. It depends on the prof. It depends on the course. It depends on the proof. This is just me the first time you've ever seen a proof going, this is what we're going to look at when we look at proofs. Something like that. Do you have any questions for me on that beautiful proof? And now you can go home and someone says, what are you doing in class? And you can say, we're doing trigonometric proofs. And that usually shuts up whoever you're talking to. They won't ask any more questions after that. There are not many people who will say much to you after you say that. What are you doing in math? Well, we're working on some trigonometric proofs. And they'll be like, huh.